I'm going to do a quick video on some fundamental particle stuff and hot Big Bang, since some of the stuff didn't get covered in the lecture that I recorded. So I want to make sure that you guys have this to study from. So in some of your first science classes, maybe you learned that atoms are the smallest thing and everything is made up of atoms. And then you took another science class later and they told you, well, atoms are made up of protons and neutrons and electrons, and those are the smallest thing. And now you're in this class and we're telling you that protons and neutrons are actually made up of even smaller things called quarks. And that's kind of the end of it, right? Unless we learn some really new things about the universe, nobody's going to tell you that there's smaller things than quarks. But I'm going to do a little overview of the types of particles that exist. So the first type of particle that we're going to talk about are called fermions. And fermions are the fundamental particles. So all of the other particles are made up of fermions, or they're just fermions. So we've got fermions. These are the fundamental particles. So, the first type of fermions are quarks. And there are 6 types of quarks. There is up, down, charm, strange, top, and bottom quarks. And they get heavier as you go this way. So up and down quarks are the lightest, top and bottom are the heaviest. Every other one has like a positive charge and then a negative charge. So 6 quarks: up, down, charm, strange, top, bottom. And then the other types of fermions, you have electrons. Those are a fundamental particle. Electrons aren't made up of anything else. You have something called a muon and a particle called a tau particle. And then every one of these 3 has a neutrino associated with it. So you have an electron and an electron neutrino. A muon, your muon neutrino. You have the tau and the tau neutrino. So every particle also has an antimatter particle. So you have an anti-up quark, an anti-down quark, or a charm antiquark, a strange antiquark. You have electrons and anti-electrons, electron neutrinos and electron antineutrinos, muons and anti-muons. So just for every particle there is an antimatter version of that particle that has the opposite charge, but the same mass. So an anti-electron, which is also called a positron, has a positive charge, but the same mass as an electron, right? Because an electron has a negative charge. So if you remember electron, muon, and tau, then each of those has a neutrino associated with it. And then everything has an anti-version, an antimatter version. And those are our fundamental particles. So the next class of particles is the hadrons. And these are made of fermions. Right, so these are not fundamental particles anymore because they're made up of smaller particles. These fundamental particles, there's nothing, these you can't break down into something smaller. They're the base ones. But hadrons are made up of fermions. You have protons, which are made up of 2 up quarks and a down quark, and neutrons, which are made up of 1 up quark and 2 down quarks. And the last type of particle are bosons, that we're going to talk about at least. Bosons are not particles in the way that we normally think of them. They are more like, hi Maxwell, they carry force and they don't have any mass. So a photon is a boson. It doesn't have any mass and it carries electromagnetic force. So you have something called a gluon, which carries the strong nuclear force. And you have W and Z bosons. These carry weak nuclear force. These are some bosons. So they are force carriers. Like the photon or the gluon. So inside this proton, there's 2 up quarks and a down quark, and they're held together by the strong force, which means that also inside this is some gluons carrying the strong force. Okay? So that is all, get down, all of the types of particles that we're going to talk about, right? So fermions, these are your fundamental particles. Hadrons are made up of fermions. Bosons are force carriers. Okay? So that is the fundamental and other types of particles. Yes. So, in the beginning, we talk about the Big Bang. So we can't really go all the way back to the very beginning. We don't know really what caused the Big Bang, what started it. But we know a decent amount about what happened right after. So, we know that the universe is expanding. So we can kind of roll back that expansion and say if the universe is getting bigger, that means a long, long time ago, the universe was smaller than it was now. And if everything inside, if the universe shrinks down, then that means everything gets denser. Everything gets closer together. And Maxwell, oh, come on. Everything gets closer together. And just like with how we learned with stars, when things get denser, everything gets hotter. So the universe, we look at the time, so since the Big Bang. So right here is the Big Bang. And this we'll say is temperature. As we go back in time towards the Big Bang, the temperature increases. So way back in the Big Bang era, it was really, really hot. And hot means there's lots of energy. So the universe had a lot of energy in this hot time. And we know from our formula, E equals mc squared, or c is the speed of light, that mass can turn into energy. Right? That's how we calculated some stuff for fusion. When you turn some mass into energy and get how much energy is released in fusion. Right? Mass can turn into energy. But if you have enough energy, it can work the opposite way too. And energy can turn into mass. But it can't just turn into any mass. It has to turn into matter and antimatter together. So in this super hot time, you had these pairs being created. So a piece of matter and a piece of antimatter. So every time an electron was created, also an anti-electron was created. And then that electron and the anti-electron would combine back and turn back into energy and back and forth, right? So you would have a proton and an antiproton being made together. A top quark and an anti-top or top anti-quark being made together. And then they would go back to, and then sometimes they would come back together and turn back into energy. So you just had all of these particles being created and destroyed and created and destroyed in this super hot, energetic time in the universe. And the more energy you have, the bigger mass of a particle you can create. So as the universe starts to cool off, there's less energy, and you can't make the biggest particles anymore. You don't have enough energy to turn that energy into the mass of these biggest particles. So as the universe cools off, you can only make smaller and smaller particles, right? The bigger ones can't be made anymore. So at some point, protons are bigger than electrons. So protons stop being made first, right? And we'll call this proton freezeout. So at this time, there's not enough energy to make new protons anymore. So we're just left with the ones that have been made already. But electrons are smaller, so there's enough energy to keep making electrons until it gets cool enough that electrons can't be made anymore. Right? So that's electron freezeout. And every type of particle has its own freezeout based on its mass. And some equations that have to do with this. So if we want to know the temperature in Kelvin at any time after the Big Bang, its temperature is equal to 10 to the 10 over the square root of the time in seconds. And then another equation is the average energy of a particle. So this is in these energy units called EV, is equal to 8.6 times 10 to the 5 over the square root of time. And again, this time has to be in seconds. So if I want to know how big of a particle I can make at a certain time, I'm going to plug my time in. I'm going to get how much energy. But remember, we're making two particles. We're making a particle and an antiparticle. So half of this energy has to go to each of them. Right? So I would plug in my time, and I would say, okay, I have this such energy. I'm going to divide that by 2 because I'm making two particles. And then that's the energy that gets turned into mass for each particle. Right? So every mass has a corresponding energy. I just multiply the mass by the c squared to get how much energy that corresponds to. And sometimes we just skip that step and just leave it as energy. And so sometimes you'll see particle masses given in these energy units like EVs. And that just means that we've taken the mass, multiplied it by c squared, and turned it into an energy equivalent. Okay? So, so protons stop being made, and then it gets cool enough that electrons can't be made anymore, and then it's still cooling down, but it's still really hot. And it's hot enough that you can have a little bit of fusion, just like we talked about in stars. You can have two protons. So a proton is a hydrogen nucleus. So if I say a proton and I say hydrogen, that kind of means the same thing, right? So you can have two protons, two hydrogen nuclei, fused together to form a helium nucleus. And you can have a helium nucleus and a hydrogen nucleus, or proton, fused together to form a lithium nucleus. But lithium is not very stable, so a lot of times it breaks back apart. And you can have two helium that come together and form a beryllium, which is also not very stable. So a lot of times that breaks back apart. So you have a lot of hydrogen, a lot of protons that get made, and then some of those make helium, and then some of those make beryllium and lithium, but some of that beryllium and lithium breaks back apart into hydrogen and helium. So mostly what you have is hydrogen and then helium and a little bit of lithium and beryllium. And the universe is still cooling off, and eventually we get to a point where it's not hot enough to do any more fusion. So this is the end of nucleosynthesis. Right, so no more fusions going on just in the universe. Right, so at the end of nucleosynthesis, we have the hydrogen that was made, some of that fused into helium, some of that fused into beryllium and lithium, and then no more fusions happening. So however much of the helium and beryllium and lithium were made at the end of this nucleosynthesis, that's kind of how much there is, right? Some of that lithium is going to decay, some of that beryllium is going to decay, but the universe is going to kind of start out with that amount, the amount that was made after nucleosynthesis. So that happens after this freeze out. And then still you've got these nuclei, you have the electrons floating around. Light is getting bounced around everywhere. So the universe is foggy. This creates that cosmic microwave background that I talk about in the section video. And eventually, things keep cooling down, and you have the electrons combine with these nuclei. So most of it is still protons. You still have 75% protons and about close to 25% helium nucleus, and then just a few lithium and beryllium. So those electrons are going to combine with the nuclei, with mostly the protons, and make neutral hydrogen and helium, and the universe becomes transparent. And this happens at 380,000 years after the Big Bang. This is not to scale. By the way, this happens like seconds after the Big Bang. This happens at like, this is like 8 times 10 to the 8 seconds. These happen even earlier on the scale of seconds. And then this is even later. So these lines are kind of not to scale. I've just been kind of drawing them on there. So the universe becomes transparent. Before, when there was electrons and protons separately around, light was getting bounced around and everything was kind of foggy. And then now they become neutral, the protons and neutrons combine, and light can shine through the universe. And so we start to be able to see, right? We can't see past here because it's just a fog. So then later on, after this, you have structures start to form. Stars start to form. Galaxies start to form. Clusters start to form. And some kind of important things to note. So I'm going to erase this. So I talked about how, kind of at the end of nucleosynthesis, our amount of hydrogen and helium is mostly set, right? There's no more nucleosynthesis happening in the Big Bang. And so that proportion, that material, that is what the first stars are made of. So these numbers are not really accurate, but I'm just going to kind of go over this to show you an idea. So say the first stars are made up of 75% hydrogen and 24% helium, and then we'll say 1% lithium and beryllium. Right, so it's actually less than, maybe less than 1% here. But I'm just using these numbers as an example. So then these first stars are made up of this. And then in those stars' lifetime, they, in their core, have fusion. So they're turning hydrogen into helium, helium into carbon, carbon into oxygen, into magnesium, into silicon, on and on and on until you get to iron. And then those stars, either if they're big enough, they explode, and if they're not, then their outer layers get shed in a planetary nebula. But either way, some of that stuff that they made gets sent out into the gas and the dust. And so the next generation of stars, they start off with not just the stuff that was made in the Big Bang, but the stuff that was made in the first generation of stars. So they start off with maybe, right, these are the first stars. So the second generation of stars has maybe 74% hydrogen and 23% helium. And now they have, 3% of lithium, beryllium, carbon, oxygen, nitrogen, or neon, magnesium, so on, and all the way up to iron. Right? So then, this is what they're made of at their start. And then they live their lives and they make more of this stuff and send it out. So then the next generation of stars has maybe, 73% helium and 22% or hydrogen and 22% helium. And now it's got 5% other stuff. And so on and so on and so on. Right? So again, these numbers are not true. Like it's not going to be this much. It's still going to be, it's going to be like 75.9 and 24.5, whatever, and like 0.7, 0.6, something, right? So, but these numbers are just kind of to show you, like, as you go back in time and look at earlier and earlier stars, you're going to have less and less of this other stuff, right? So early stars, the older stars, should have less of this heavier stuff, this stuff that's heavier than helium as you go back in time. If we're right about this whole Big Bang thing. And they tested it, and they've looked at the older stars, and they see that it's true. That stars that were created much longer ago have lower amounts of elements that are heavier than helium than stars that are born more recently. Okay, so another thing that's kind of interesting is when the universe was less expanded, so after the first galaxies had formed, which was about maybe like a billion years after the Big Bang. So it's been 14 billion years about since the Big Bang. And 1 billion years after the Big Bang is around when the first galaxies started to form. And everything was closer together then. You had all the galaxies, and the universe was smaller, so galaxies were closer together. And because they were closer together, that means that it was really a lot more common for galaxies to merge together. Because they're closer together, they're going to bump into each other more often. And that led to a couple interesting things. So, one thing, there was more star formation during this time. So, more mergers. When two galaxies bump into each other, their gas and dust mix up. You have a lot of gas and dust coming together, and that is prime time for star formation. So there was a lot of star formation in the early universe, and the amount of star formation has gone down over time. And then another thing that happened is when two galaxies merged together, they would have some like a black hole in the center of these galaxies. And we talked about the black hole in our own galaxy, how it's basically just sitting there, not doing anything. But the black holes in some other galaxies have these accretion disks around them, right? They have gas and dust being sent into the black hole. And as this gas and dust spirals around the black hole, it gets really hot. And it sends off, X-rays. And sometimes they have big jets coming out of them. These are these active galactic nuclei, also called quasars. And so when you had merging galaxies, then this merger would push a lot of material in towards the black hole. And so you would get these accretion disks, and you would get more quasars. So there was a lot more quasars around like 1 to 3 billion years after the Big Bang than there are now. So you get more star formation, more mergers, more quasars in the early time. And then since then, things have spread out more, and we don't have as much of that. So I'm going to go over some of the homework problems. So 1 and 2 I do in the math video that is put up. And so let's look at problem 9. It says, which of the following are true and which are false? So the first one says the total star formation rate in the universe has been relatively steady since about 1 billion years after the Big Bang. And that is false. The total star formation rate has gone down. You had more mergers, more star formation in the early part of the universe. And like, when I say early, I mean, about 1 billion years, starting 1 billion years after the Big Bang. So the second is quasars are much more common in the period between 1 and 3 billion years after the Big Bang than they were before or after that time. That is true. We had more mergers, more quasars. The merger rate of galaxies has been steadily increasing over time as the universe expands. That is false. We used to have more mergers back when everything was closer together. And the last one says that dark matter is much more common than the type of matter that makes up stars, planets, and humans. That is true. That's something I talk about in the section video. But dark matter, there's a lot more dark matter than there is normal matter. The universe is made up of like 70-something% dark energy, and then close to like 25 or something percent dark matter, and then only like 5% normal matter, like that we're used to, that makes up stars and you and me. So there's a lot more dark matter. So 10 says, which of the following are fundamental particles? The proton is not a fundamental particle, right? It's made up of quarks. Electron is a fundamental particle. It's a fermion. It's not made up of anything else. The hydrogen atom is not a fundamental particle. It's made up of protons and neutrons and electrons, or proton and an electron, and the proton itself is made up of quarks. So a neutron, again, that is a hadron. It is made up of quarks, so it's not a fundamental particle. The up quark, that is a fundamental particle. It's a fermion. Nothing makes up an up quark. It makes up other things. The positron, which is an anti-electron, that is a fundamental particle. And the electron neutrino is also a fermion, a fundamental particle. So problem 11 is another one that I do in the math video. We're going to use that formula that I said before, where temperature is equal to 10 to the 10 over the square root of time to find out the temperature at a time in the universe, and to get the average energy, use the formula 8.6 times 10 to the 5 over the square root of time. So if you want to see those worked out, as well as problem 12, those are in the math video. And then 13 says, where's the formation site for each of the following elements? It can be equilibrium fusion in stars, supernova 2 explosions, or the hot Big Bang. So the first one is hydrogen. Hydrogen is only made in the Big Bang, because hydrogen is just a proton and an electron. Those are only made in the Big Bang. Fusion can't make hydrogen because it's just like one proton. So you can't have two protons coming together to make hydrogen because it's just a single proton. So all the hydrogen in the universe was made in the Big Bang. Unless it's something else like breaking down into hydrogen, but all the base hydrogen in the universe was made in the Big Bang. So thorium. Thorium is something heavier than iron. And specifically, it's made by the R process, which is the rapid addition of neutrons. So in order to make thorium, you need some place where there is a lot of neutrons. And one of those places is when a neutron star is forming, which happens during supernova 2. So thorium is B, supernova 2 explosions. Iron, that is the last step in the equilibrium fusion of stars for heavy, high mass stars. So iron is made in A, equilibrium fusion of stars. And then helium, so we talked about Big Bang nucleosynthesis. Helium is made there. So helium is made in the hot Big Bang. But also, when stars fuse, they turn hydrogen into helium. So helium is made both in the Big Bang and in equilibrium fusion in stars. So A and C are for helium. 14, that is about nucleosynthesis. I go over that in the math problem. And then 15, what was the nature of the transition in the universe that occurred around 380,000 years after the Big Bang? That is when the electrons joined up and recombined with the hydrogen nuclei, and the universe became transparent. It stopped being foggy, and light could pass through it. 16 says, which of the following provides supporting evidence for the hot Big Bang model? So the abundances of elements heavier than helium are lower than the solar values in older stars. And that's true. That's what I talked about when I said that old stars have less stuff that's heavier than helium, right? Because it's made in the stars. So every time you go back in a generation, you have less to start off with. The predicted abundances for helium-4, helium-3, hydrogen-2, and lithium-7 at the time of element freeze-out, around 300 seconds after the Big Bang, match observations. And that is true. We can predict, after all this nucleosynthesis and stuff, we can say how much of those we expect to have, and then we can measure how much there was back then, and it matches up pretty well. The presence of a ubiquitous background radiation characteristic of that from a 3K solid, that is also true. That is the cosmic microwave background that I talk about in the other video. It's when the universe was foggy, it was 3,000 Kelvin. It looked like a solid, this big foggy solid, and then the light from that, as it gets to us, has been redshifted by cosmological expansion, and by the time it reaches us, the light, that redshift has made the light look like it came from something that was a 3 Kelvin. So I say 2.7 sometimes, 2.73, it's just rounding. And then fluctuations of about 1 part in 100,000 in the temperature of the cosmic microwave background. That is also true. That cosmic microwave background, we need fluctuations in the temperature in order to get structure, in order to make galaxies, in order to make galaxy clusters, and all the structure that we see in space right now. If there weren't fluctuations, then we wouldn't have that. So we expect to see those fluctuations, and when we look at the cosmic microwave background, we do see them. So I talk more about that in the other video. 20 says, which of the following are true and which are false? The merger rate of galaxies has been steadily increasing over time as the universe expands. That is false. We had more mergers early on when everything is closer together. And dark matter is much more common in the universe than the type of matter that makes up stars, planets, and humans, also called baryonic matter, and that is true. Okay, so one correction. I said earlier that the end of nucleosynthesis, I said it was around 8 times 10 to the 8 seconds. That is wrong. It was about 300 seconds after the Big Bang when that happened. So ignore what I said earlier. Okay, so that is some fundamental particles and some Big Bang stuff to kind of supplement the other video that I put up. And that should be most of the material needed for this quiz. So there's also the video of all the math problems from this quiz that I put up as well. I hope that these have been helpful to you. Please take a few minutes if you have time and fill out the evaluation forms for this class and for the TAs. I would very much appreciate that. I like to get feedback and know things that I'm doing that are working and ways that I can improve. So please fill those out, and good luck studying.